Okay, class, we're covering section 2.5 on page 189. It's called the Great Tech Battle. Our learning objectives is to determine whether two variables have a linear relationship, to calculate the line of best fit for a set of data using a spreadsheet, calculate the line of best fit for a set of data using a calculator, and to interpret the correlation coefficient for a data set. It says one machine can do the work of 50 ordinary men. No machine could do the work of one extraordinary man. Elbert Hubbard. The quote says an awful lot about the dangers of too much reliance on technology, a peril with the potential to affect every modern student. The most interesting thing about it, though, is that it was written in 1903. When used correctly in math, technology allows us to focus more on understanding and interpretation and less on computation. That's great. But when you try to use any technology as a substitute for thinking, nothing good is likely to happen. In this lesson, we'll learn how technology can help us to decide when a given data set is likely to be modeled well with a linear equation. Better still, calculators and spreadsheets will be able to find the best linear model for such situations, freeing us to focus on interpreting the model and using it to further study the data. Okay, now if you look here, we have this calculator shown here. And of course, this does not look like Desmos, but this is actually a TI-84 calculator, which was the calculator typically for this. Now, let's look down here. It says in lesson 2.4, we examine the relationship between calories burned and weight loss. While we needed to study data to model the exact nature of the relationship, you were probably able to figure out that the two quantities are related in some way. There are many quantities that seem like they might be related, but it's not clear that they really are, or if so, how. So it would be nice to have a way to study relationships, if they even exist between data sets. Fortunately, the lovely folks who program spreadsheets and graphing calculators have done most of the heavy lifting for us. Still, in our continuing quest to not rely on technology more than our brains, it's a good idea to think about when quantities are likely to be related in some way. Number one, decide if you think the two quantities are likely to be related numerically and explain your answer. Okay, A. It says dollars spent by a political candidate and the number of votes he gets. Okay, now basically spending a lot of money does have an influence on the number of votes. Okay, B. An adult test subject's height and IQ test. Okay, there's actually no reason to believe height affects IQ. Okay, now we go to the next page. We have C, a person's height and shoe size. Okay, larger people do tend to have a larger shoe size. Now, D, the age of a car and its resale value. Okay, most cars are worth less as they age. Now, there's only a certain amount of cars that is worth more, and those are vintage cars. Okay, now, Number 2, it says, is there a relationship between the total fat in a fast food burger and the total calories? The table here lists calories and fat information for a standard hamburger at a variety of fast food restaurants. Begin your study of the question by drawing a scatter plot based on the table. So basically, they're taking a basic hamburger and comparing the fat and calories. Okay, now if you look down here at this graph, they basically do some of the work for you. The X value and the Y value. Tells you here the X value is the grams of fat, which here is total fat in grams, and then the Y value is calories. Now, I don't believe anyone in here is using the TI calculator, but if someone is, please let me know. Is anyone in here using the TI calculator? All right. Okay, let's see. All right. So I'm going to do this in both calculators. But first, I'm going to do it in the Desmos calculator. So we're at the plus, and we'll go to the table. And then in the X, we'll type in all of the X values. So we had 9, we had 12, we have 8, 12, 17, 15, 7, 14, 14, and 19. Okay, now type in the calories. We had 250, 290, 230, 310, 470, 310, 140, 350, 310, and 390. Okay, so now we typed in these values. They asked us, let me see, they asked us to draw a scatter plot here. So we could take these values and put these values in our course pack here, and we could graph them. So we start here at basically, let's go here to 9. 9 is like right here in the center between 8 and 10. So 9 would be 250. We will go up here to 250. And then we would do 12 to 290. 290 would be real close to 300. Then we would have 8 and 230. Should be about here close to the middle, a little bit above the middle. Then we would have 12 and 310, a little bit above the 300. 17 and 470, a little bit below half. 15 and 310 should be a little bit above 300. Okay, then 7 and 140. Let's see, 7 and 140 should be about here. 14 and 350. And then we have 14 and 310. And then we have 19 and 390. Be about here. Okay, this is our scatter plot. And then they ask us to, basically what we want to do is do a line of best fit. Well, that actually comes in the next problem. Let me go here to number 3. It says the points on your scatter plot don't form a straight line, but there should be a linear trend you can observe. Use a straight edge to draw a line that you think looks like the best fit for your scatter plot. Note that it's possible that the line that fits the data best doesn't go through any of the points. All right. Let me see if I could grab a quick ruler. Here's one. All right. So let's see. So we could do our own little line here, best fit. All right. Now, oh, I'm sorry, I didn't show that. Yeah, this is a line, a possible line of best fit here. Okay, now it asks us for problem number 4. It says identify 2 points on the line of best fit that you drew on your scatter plot and use them to find an equation for the line. Okay, now when I look here, I actually hit 1 point. This was 12 and it looked like 12 and yeah, 290. So 1 point would be 12, 290. Now yours may look a little different than mine, but we're just grabbing 2 points from what we see. And I would see that, let's see, does it hit any other place exactly? It actually hits here at 7 and 200. Okay, so those are my 2 points. All right, so now we're going to do a slope. Okay, and we're going to try and get the equation of best fit here. So we have y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. So this is negative 90 over negative 5. Negative 90 divided by a negative 5 will give us 18. Now, a lot of times your answer is not going to come out this exact, but I'm just saying since we're just using points off of the graph. Now, I want to tell you this here, an easy way of possibly doing this. Since we have the slope, we know we want to get to y equals mx plus b. That's what we want to get to. So what we could do is we could pick one of these 2 points. I'll pick the second point, and then we could take the slope. So y here would be 200. The slope would be 18, and x would be 7. So it'd be 200 is equal to 126 plus b. All right, so we'll subtract 126 on both sides. So 200 minus 126 is 74, and it equals to b. So now we have our m and we have our b. So our final equation would be y is equal to 18x plus 74. That would be our equation. Okay, as you've just discovered, we can use a couple of points on a line and some algebra to find the equation of a line of best fit for some data. Then, as we'll see shortly, we can use that equation to study the quantity. But the weakness in this process is that the line of best fit we drew is just a guess that we got by eyeballing the graph. Fortunately, calculators and spreadsheets have built-in formulas that will find the exact line of best fit for a given data set. The procedure is in the following box and is illustrated by the solve example. All right. So what we're going to do, we're going to skip over this solved example and going to go through and try and do these problems ourselves based upon our given data. It says use the procedure and using technology box to find the equation align the best fit for the fast food burger data on page 190 using the graphing calculator. Now it tells us to round to 1 decimal place. Now I'm going to show you how to do this on Desmos because that solve example only shows you how to do it on the TI calculator. Now Desmos, if you look here, we're looking to get a straight line, so we're doing linear. Now we know the linear formula is this here, y equals mx plus b. Okay, we know that's the linear formula. But what we have to do, and let me do this here. Let me take this in so I could see. As a matter of fact, let me just change this real quick. So I want you all to see these points. So let me see. The lowest on the y-axis was like 7 or something. So I mean the x-axis, the lowest was 7, so I make that 0. Then the highest on the x-axis, I think, was like about what? 19, so I make that 20. So I make that 20, and then the y-axis, the lowest on the y-axis, based upon our table on page 190, the lowest on the y-axis was 140, so I just make it 100, and then the highest was, what's that, 470, so I make it 500. Okay, now that I did that, now we can see this graph a little better. In fact, let me expand this. We can see this graph a little better here. Those are our points. Now, getting back here where I said that we had the y equals mx plus b. All right, now we have to redo this to show this on the Desmos calculator. Okay, so what we will have to do is, first of all, if you look up here, we got y1. So this y must be y1. Okay, now the next thing, the equal sign. We're going to replace the equal sign. We have to press this ABC. And I still don't know why this is going so slow. And we have to click on this tilde symbol here. And we could get rid of our equal sign. Okay, now x has a 1 with it. And now we have what we need. If you notice here, we have a graph. I could even go further. And we can see our graph here and our line of best fit. Now, they want us to get the equation from here. Now, we know our equation is y equals mx plus b. Now, all we have to do is get the slope, which is shown here, and we round it to 1 decimal place, so it'd be 20.8x plus b. b is 41.4. So that is our equation, 20.8x plus 41.4. Now I'm going to pull up the graphing calculator. Let me pull that up real quick, or as quick as this computer will go today. All right, let me move this over here. Okay, so I'm going to take the same information. Yeah, I think this would be good right here. I'm going to take the same information and I should get the same values for my slope and y-intercept. All right, so first thing, I would have to press stat. And then as you see edit, I'll press enter. And then we had L1 and L2. L1 represents X, L2 represents Y. So now we would type in the values. We had 9, enter, 12, enter, 8, enter, and then we type in all of the rest and press enter after each number, and especially after that last number. All right, now I have to go back up here and type in the rest of the numbers. 50, 290, 230, 310, 470, 390. Okay, now we got all the values in. So the next thing we would do is press second in mode. Then we will go back to stat, go to the right to calculate, just one place. And we will go down here to the number 4. Now you can either go down to the number 4 and press enter, or you could just press the number 4. So that would be for your linear regression. I'll press enter. Okay, now your X list must have L1, your Y list must have L2. Now this frequency list and the store regression equation, both of these should be empty. And so you go down to calculate and press enter. Now it gives you your A and B. And if you round this to one decimal place, this would be 20.8 and 41.4, which is what we got here. So it does work. All right, now number 6 says use your answer to question 5 to predict the number of calories in a Whataburger, which has 25 grams of fat. How does the answer compare to the number of calories predicted by your own line of best fit? In question 4, the Whataburger actually has 590 calories. Which line gave a more accurate prediction? So first, we're going to go with this equation here. And we're going to put in the grams of fat, which would be 25 plus 41.4. So we would have, this will end up giving us 561.4 calories. Now, going back to the formula that I had got, my formula was y is equal to 18x plus 74. Now we'll put in 25. So 18 times 25, let's see, what's that? 450 plus 74, which is 524. All right, and they say here that the Whataburger actually has 590 calories. So the equation we have from number 5 is more accurate. All right. Now we move on to the next page. It says a classic roast beef sandwich from Arby's has 360 calories and 14 grams of fat. What is your line of best fit predict for calories? Is this expected? Explain. Okay, so we have to use the formula that we had, which is y equals 20.8, and it's times 14 plus the 41.4. So y would end up being 332.6 calories. Okay. Now it says, what is your line of best fit? Predict for calories. We have that. Is this expected? And it'll be yes, because roast beef usually has less calories than hamburger. Okay, now when finding the line of best fit using a graphing calculator, the last line in the display should be a value for a quantity labeled R, which is known as the correlation coefficient. If your calculator is not displaying R, press second, 0, then use the down. Okay, now this is talking about the TI-84. So let me do that real quick, because as we see here, R is given with Desmos. That's automatic. But with the TI, you notice the R is not displayed here. So for those of you that use the TI calculator, you will press second, then 0. Then you will press this X to the -1 key to get to the D, and you will go down until you get to diagnostic on. Because if you notice, diagnostic off comes first. So you will go to diagnostic on and press enter, and then enter again. Now it says done. So if you go back, go to calculate, the number 4, go down here to calculate, and now it gives you the R value. If you notice, this R value is the same as this R around in the 4 decimal places. So now that we see how to get that on the TI calculator, we could just go ahead and focus on the Desmos for right now. Now we have these graphs here. It says this number measures how well the line seems to fit the data. The closer R is to 1, which has a positive slope, or -1, which has the negative slope, the more accurately the data you enter can be modeled using a linear equation. Here are some examples based on data from 2 of my classes last semester. Okay, now we look here at the data. Now we go here to problem number 8. It says one of these scatter plots has a correlation coefficient of 0.19. The other has a correlation coefficient of 0.82. Discuss which you think is which and why. Okay, now, whichever one of these looks more like a straight line will be the one that will have the higher correlation coefficient, which seems to be this one here. The one to the right is more scattered. So we would say the one to the left would have the 0.82 correlation coefficient. Because this graph looks more like a line with a positive slope. The other graph is more scattered and would have the 0.9 correlation coefficient. Okay, number 9. One of the scatter plots has each student's homework score for the semester on the x-axis and the corresponding overall percentage in the course from 0 to 100 on the y-axis. The other again has overall percentage on the y-axis, but along the x-axis is the student position alphabetically in the class. The student whose name comes first alphabetically is 1, the next alphabetically is 2, and so on. Which plot is which? Again, discuss your reason. All right. We have to say that the first plot has to be the relationship between homework and overall percentage. It stands to reason more homework, well, I should say doing more homework will help you learn and your overall grade will improve. And then just to get on a fact about the name of that, there is no way to prove the first letter of your name will improve your grade. Okay, now it says, what is the value of the correlation coefficient R for the fast food sandwich plot? Round to 2 decimal places. Now, if we look here, R, we got 0.8984. They asked us to round to 2 decimal places. So R is equal to 90. I should have put the approximation symbol. It would be approximate. All right. Now we come to the next page. Number 11. It says, based on all of the work done in this activity, how strong do you think the relationship is between the number of grams of fat in a fast food hamburger and the number of calories in it? It's very strong. The scatter plot shows a clear pattern of the data points which almost forms a line. And the correlation coefficient is close to +1. Okay, now it says here, hopefully you noticed right from the beginning of our study of burgers that you can't draw a straight line that goes exactly through all of the points. That in turn means the predictions made by our equation for any sandwich are unlikely to be perfectly accurate. This will almost always be the case when finding a line of best fit for a data set with more than two values. There's a good reason we call it the line of best fit, not the line of perfect fit. The equations we're finding are models for data that allow us to make approximations and predictions. They're not exact representations of data. Now, number 12, look back at the original table of fat and calories near the beginning of this lesson. Use the calculator generated line of best fit to predict the number of calories in the Hardee's burger. Then find the difference between the actual number of calories and the predicted value. Okay, so we go back here. The Hardee's burger, this is on page 190. The Hardee's burger has 12 grams of fat and it's 310 calories. Okay, so we go to our line here and we try and find where the line has 12. And we could just drag here till we get to 12 or close to it. So it's like, it's a little over 290 calories. So we could say 290 calories. So we could say the prediction was 290 calories, and the actual is 310 calories. The difference is 20 calories. Now, it says when using a line of best fit to model data, we use the term residual to refer to difference between predicted values obtained from a model and actual values. You just computed the residual for the Hardee's burger. Remember, the output we get from the equation of the line of best fit is the predicted value. So when a data set is modeled by a line of best fit, the difference between the actual value from the data set and the value predicted by the equation is called the residual for the value. So residual is equal to actual value minus predicted value. The sign of the residual tells you if the actual value was higher, positive residual, or lower, negative residual than the predicted value. Find the residual for the White Castle burger. Now, we go back and we look here at the White Castle burger. Now, if you notice, the White Castle burger is 140. That is the actual. So we go here to the graph. It was at 140. So we go here to the graph and we go up here till we get to, let me see, it's not letting me drag here. Now there actually is another way to do it. I don't know why it won't let me drag. Oh, okay, here we go. All right. It's actually this computer is very slow today. So if you notice here at 7, we got 186.686. So we could round that to 187. So the actual value, so the residual is equal to the actual minus the predicted. The actual was 140. The predicted was 187. So it's a negative 47 calories. So actually we went over about 47 calories. Okay, so now we just finished section 2.5, and now we're about to go to section 2.6. So let us go on over to lesson 2.6. You never know, we might actually make it to 2.8 today, but that might be pushing it. So let's just see here. All right. Now this looks up our alley here. It says sit back and watch your money grow. All right, our learning objectives. We are to define, function, and use function notation. Identify the significance of a and b in an equation of the form y equals ab to the x power. Find exponential models. Compare exponential models using graphs, tables, and formulas. It says if I take 30 steps linearly, I get to 30. If I take 30 steps exponentially, I get to 1,000,000,000. Ray Kurzweil. Raise your hand if you hope to be rich someday. There's a pretty good chance that your hand is up right now. Financial independence is a goal for a lot of people. We've already studied the differences between quantities that grow linearly and those that grow exponentially. Now that our skills at interpreting graphs have grown, well, exponentially, it's a good time to revisit exponential growth to learn a bit more about its magic. We already know that the long-term growth of money is an ideal way to study exponential growth. So we'll start there, and on the way, start you on the path to riches. Now we come down here to number 1. Describe the differences between linear and exponential growth based on what we know from earlier in the course. Okay, linear growth is steady and does not change. Now, and just to get a little bit more descriptive, the new amount comes from adding the same amount each time. With exponential growth, just give me 1 second here. All right, with exponential growth, the rate increases at larger amounts. The new amount from multiplying the previous amount. By the same thing. All right, now let me give you a real life example. And I know have you all heard of that old saying about if you take a penny and double it for 30 or 31 days, you would be a millionaire? Have you all heard that before?
Yeah.
Okay. Well, let's take a quick look at this. Now, what I'm going to do, I'll pull this up online to make this a little easier. Let me see. Doubling penny for, let's do 30 days. See if I can pull that up real quick. Let's see, there was, oh, here's the chart right here. Now this, it has all 30 days. And if you notice here, every time you're multiplying by 2, and it gives you all the way up to 30 days, which would be 5,368,709.12. Now, of course, if you do the 31st day, you would be over $10 million. Does everyone follow that? And that's just from doubling the penny every day. Now, if you just was to add a penny every day, this would go 1 to 2 cents, then 3 cents, then 4 cents, and so on. So you wouldn't even have, let me see, you wouldn't even have $1 after 30 days if you just added a penny each day. Does everyone follow that? So that is the difference between exponential growth versus the linear growth. This is an example of exponential growth. So I guess you all need to get those pennies together, and you all could be rich one day. All right.
Hey, Mr. Gibson. So I'm currently in the college parking lot because I have a class right after this, and I don't know why, but my laptop has been overheating and the battery has been like draining, and I'm gonna need my laptop for my next class. So is it fine if I leave the class now to make sure that I have enough battery for my next class and I can just catch up on the video?
Okay, have a wonderful day.
All right, thank you.
Okay.
Have a good one.
All right, now we go on to the next page, page 208. Okay, actually, just to let you all know, we're only going up to page 215, and then we will be done with 26. It says here, most people won 15,000 on a game show. They go on the spending spree, but not you. You're too smart for that. Instead, you decide to invest that money to make it grow. I'm not sure how patient you are, but what if you were super patient? Like patient enough to let that money grow for 40 years in a fixed rate investment. Let's take a look. Make sure that you answer every question with a complete sentence. Now, if you look here at this graph, it's more curved. This is an exponential graph. Now it says for each value in the table, after the initial investment, divide the amount by the value of the account the previous year. What do you notice? So basically what they're saying is, they're telling you to take this amount divided by this amount divided by this amount, and so on. So basically, in each case, the result is either 1.07 or very close. And the reason for that is this here. Remember, in our number system, we stop at 2 decimal places. So there are instances where this had to be rounded. That's why it would be a little off from the 1.07. But just to show a quick little example of this, I'm just going to do 2 of the numbers. So I'll do that 16,050 divided by the previous year, which would be 15,000. And that gave you 1.07. And then I would do the 173.50. And that'll be divided by that 16,050. And that gave us 1.07. So if you keep doing that, you're going to get 1.07 or something very close. Now, number 3, what does your result in question 2 say about the type of growth this account exhibits? This shows that the value of the account is multiplied by 1.07 each year. Which makes it exponential growth. As we know, we're not adding 1.07 each year. So we're multiplying 1.07 each year. Now it says find the relative change in value for each year in the table compared to the previous year. What can you conclude? Okay, listen. The relative change is 7%. This shows that the account grows by 7% each year. Okay, now let me show you how we would know that it grows by 7% each year. Okay, remember we do percent increase divided by percent decrease. Now, if we take this value here, remember, the original of this value would be the 16,050. So we would take the 17,173.50 minus the 16,050 and divide it by 16,050. And we would do that for the previous one as well. Remember, we had 16,050 minus the 15,000. And then it'll be divided by the 15,000. Remember, it's new minus old divided by old, or new minus original divided by the original. And then we would change that decimal to a percentage. That's how we get the 7%. Now, number 5, it says find the value of the account after 10 years. Don't multiply by 1.07 10 times. That's what exponents are for. So remember, we would take our initial investment, which is 15,000, and we know to get the next year, we'll multiply by 1.07. That's only for 1 year, but we want to do it for 10 years. So we would take this to the 10th power. And when you put this in your calculator, you have 15,000. You could do the parenthesis 1.07, close that parenthesis, and then take it to the 10th power. And it would give you $29,507.27. Now, number 6, it says use your answer to question 3 to write an equation in the form y equals expression, where the expression describes the amount of money in the account after X years. Okay, so in this case, we start off with $15,000. That's what we started off with. We know we're multiplying it by 1.07 in order to get the value for each year. And then X will represent the amount of years. So this is our formula here. Now, we move on to the next page. It says verify that the equation you wrote generates the account values in the table. Ideally, you will use the table feature on either a graphing calculator or a spreadsheet. But in any case, make sure you describe how you got your values. Okay, now we're going to type this into Desmos. So we have y is equal to 15,000 times the parenthesis of 1.07, and we would take that to the x power, to the power of x. Now, once we get here, we want to make sure that we generate the results from 0 to 7, which we had here. It was from the 0 year to the 7th year. So what you do, you will click on this wheel up here, and you will come down here to the formula, and you will hit the table, convert the table. Now, if you notice here, we have some values here, but you could type in the other values. You can go all the way to 7. And as you see here, the values we have does mirror what we have in the textbook. We just have to round to 2 decimal places. And that's it. So we did prove that from 0 all the way up to 7. All right, now it asks us to describe it. We could say using Desmos and converting the equation to a table. We get the same results. Now, as far as graphing this on a spreadsheet, you could read that at your leisure. It's right down here in the middle of page 209. But I want you to look at this tan box here. It says a function is a relationship between two quantities where each input produces a unique output. So basically it's saying that where each x value, where each x produces a unique y. That's basically what it's saying to you. So basically, you cannot have the same x value. If you have the same x value, which is your input, it's not a function. You can have the same y value, but you cannot have the same x value. All right, now, say function notation. The output of a function named f is described by the symbol f of x, which is read f of x. Warning, never read f of x as f times x. It's not a multiplication. Okay, listen. I'm going to say this here. Well, I'm going to write this here so you can have this in your notes. F of x, g of x, and h of x. All of these of x's is the same thing as just saying y. So h of x, g of x, and h of x is basically just replacing y. So wherever you have a y value, it can be replaced by one of those function notations or any other letter that denotes of x. So it says, so we will write the investment equation as f of x is equal to 15,000 times 1.07 to the x. Now remember, we had talked about this too, that the f of x is the same thing as saying y, because remember we had y is equal to 15,000 times 1.07 to the x. So now this gives us other terms as far as using the Excel formulas, and you can read that at your leisure. But let's look down here at number 8. For the spreadsheet displayed earlier, find the output for the function sum b of 3, b of 4. Now, we're not actually going to Well, let me take a look here. Let me go back to that page. You may have to do a little bit of that. All right, so listen. In the spreadsheet, you had A and B. This first line here, this would be A1, and A1 would be player. B1 would be score. A2 would be Casey Petty. B2 would be 69, and so on. So they ask us here to get the sum of B3 and B4. This is how you would write this in an Excel file. So they're asking us to add B3 and also B4. So we would have 73 plus 75 is equal to 148. That would be the answer for number 8. Now, number 9, it says for the function describing the value of our $15,000 investment, find f of 12. Okay, so find f of 12 and describe what it means. So we will have f of x is equal to 15,000 times 1.07 to the x power. That's the formula we're using. Now they're telling us in this function to replace x with 12 wherever x appears. So this would be f of 12 is equal to 15,000 times 1.07 to the 12th power. Now we already have this equation set up in our Desmos. So what I could do is just type in 12 and it will give us our answer, which would be $33,782.87. Because remember, we only go 2 digits behind the decimal place. Now, we move on to the next page. It says here, look back at the graph that illustrates the value of the account. Trace along the graph slowly from left to right and describe what the change in steepness of the graph tells you about how the value is growing. So they want us to go back to this page here. And if you notice as we go along, it starts growing faster and faster. That's what the steepness is. It's getting steeper and steeper more quickly as we go on. So basically, as we go on, the graph gets steeper faster. So it says here, how much interest will you earn from 0 to 5 years into the investment? This will be the difference in the value after 5 years in the initial investment. You could use the formula for the function, but the table of values printed earlier is a better choice. Okay, so basically, we would take the 15,000 that we started with, and then we would go to the 5th year here, and that'd be $21,038.28. And then we would subtract the 2, and that means you would make interest of $6,038.28. I'll put the dollar signs here. Okay, that's how much interest you made here. Number 12, how much interest will you earn between years 35 and 40? So we'll type in 35, and then we'll do 40. So we have between years 35 and 40. So we'll take the 40th year, which is $224,616.87, minus the 35th year, which is $160,148.72. And when you subtract those two, you end up with $64,468.15. Now, both of these are 5-year periods, but as we said earlier, The longer you go with this, the higher your interest is going to be. This is over 10 times more interest from years 35 to 40. Now it says describe what you can learn from comparing the answers to questions 11 and 12. Also describe how that fits in with your answer to question 10. All right. So basically, the amount of interest earned in the first 5 years is 10 times less than the interest between years 35 through 40, which shows as time goes on, the interest increases at a faster rate. All right, we move on here to the next few pages. Now, it says here, these next few pages, they're not that long. It's just a lot of reading, but it's not that bad. Okay, so it says we've now studied exponential growth a couple of different times in this course, but there's a flip side to exponential growth known as exponential decay. The thing that distinguishes exponential growth is that the growth starts off relatively slowly, then speeds up dramatically as time passes. Let's see how exponential decay compares. Coffee is a popular morning drink because the caffeine it contains acts as a temporary stimulant. Once the caffeine gets into your system, the amount dissipates exponentially, assuming that you don't add more, of course. Answer every question except for 2 and 6 with a full sentence. Okay, number 1. You're the coffee drinker represented by the table and graph. How much caffeine was initially in your system? So we could say there was 180.0 milligrams in my system initially. I should have said of caffeine. Yeah, I should have said there was 180.0 milligrams of caffeine in my system initially. Okay, number 2. It says find the relative change in caffeine for each 1 hour period listed in the following table. Round to the nearest percent. So they're saying from 0 to 1. So 0 to 1 hour. So what we would do here, we would take the value from the 1 hour, which is 144. Then we would subtract the beginning hour, which was 180, or the 0 hour. Then we would divide it all by 180. And if you notice, we have a negative 0.2. So we'll change that to a percent. So it'll be a negative 20%. Now we will go from 1 to 2. Now I'm not going to do all of these, but I am going to do the 1 to 2. So it'll be 115.2 minus 144 divided by 144. Now it still should be a negative 20%. All of these should give you a negative 20% or very, very close to it. Now, if you need to, since I did this in the calculator, you could write out, well, I'll write out 1. So I take 144.0 minus 180.0 all over 180.0. And I'll just put 0 to 1 to show that. And then 1 to 2 would be the 115.2 minus 144 all over 144. And that'd be a negative 0.2, which is a negative 20%. Just to show you a couple of examples. Okay, now we go on to the next page, which is page 213. Now, number 3, it says, complete the important statement about exponential change. A quantity either grows or decreases exponentially when the relative change in that quantity is constant. Now, looking at the graph of the caffeine remaining in your system, describe what exponential decay looks like compared to exponential growth. So the amount decreases rapidly at first, then slows down or level off. The opposite is true for exponential growth because it starts off slow, then grows rapidly. Number 5, what's the multiplication factor that you need to multiply by a previous hour's amount to get the next hour's amount? Hint, if 10% of something goes away each hour, 90% remains. So 20% is going away each hour. So you would need to multiply by 0.8, and I'm going to put in a parenthesis 80%. So you would know that that's what we get in the 0.8. 80% because each hour loses 20%. Well, I guess I should put from the previous hour. From the previous hour. Now, number 6, it says use your answer to question 5 to write a function of the form f of x equals the expression, where the expression describes the amount of caffeine left in your system after x hours. Your answer to question 6 in the class portion is a good place to look if you need help. Okay, listen. F of x, we know we start off with 180. Now, the only thing that we have to worry about is what will go inside this parenthesis. Remember how we said that each hour will be multiplied by 0.8 or 80%? So that is what goes into this parenthesis. Anytime you have anything inside this parenthesis that's less than 1, then that lets you know that you're doing exponential decay. Anything less than 1 is exponential decay. Okay, now we move on. It says here, use a graphing calculator to verify that the equation you wrote in question 6 gives you the values in the table and the given graph. Describe your results. Okay, just like we did before, we would type in y is equal to 180, then the parentheses 0.8, and then we would take this to the x power. All right. Now, let me turn off this graph. You could turn off graphs by simply clicking like here, here, here. And so now the only graph will be this graph here. So now we want to prove this table just like we did before. You'll hit the wheel and you'll go down here to your equation and hit the table, convert the table. And as you see here, we do have the graph. And then you could put in values. It only went from 0 to 7. So we'll do 3, 4, 5, 6, and 7. And if you notice here, this gives you the exact same amounts. If you round to one decimal place, it's page 212. So basically for number 7, it says describe your results using Desmos and converting the equation into a table. We see we get the same results. Okay, number 8, use the function you wrote to find the amount of caffeine left in your system after 150 minutes. So our equation was y equals 180 times 0.8 to the x. Now they want us to see how much is left in our system after 150 minutes. Now, we can approach this a few ways. First of all, one way we could do this is first of all write this as a function because it should be f of x equals 180 times 0.8 to the x. Okay. Now, our next step, 150 minutes. We have to look at this in terms of hours because in our table, everything is done according to hours. So we have to change 150 minutes to hours. Now you could take your Desmos calculator and you could take 150 divided by 60 because this was one of our conversions. It's 60 minutes in an hour. So 150 minutes divided by 60 minutes will give you 2.5 hours. So I write that up here, 2.5 hours. So we have f of 2.5 is equal to 180 times 0.8 to the 2.5 power. So when we put this in our calculator, after 2.5 hours or 150 minutes, this will give us approximately 103 milligrams. So we'll say the amount of caffeine left in your system is 103 milligrams. All right, number 9. It says use the graph to estimate the amount of time needed for the amount of caffeine to drop to 40 milligrams. All right, so what we could do here, actually, let me see this here. I have to scoop this table up a little bit. All right, so we want to drop this to go about to 40 milligrams. Oh, it won't let me drag on here. Oh, all right. Let me show you this because I will have to show you this eventually anyway. All right. Whenever you change an equation to a table, it doesn't let you drag on the graph. So what you could do, if you could just retype the same equation, that'd be y equals 180 times 0.8 to the x power. Okay, once you do that, oh, I put 1800. Okay, so it'd be 180. Okay, once you do that, now you should be able to, oh, okay. Now you should be able to start dragging this until you get to where y is 40. Just keep going down. It's not going to be exact, but you will be very close. Like 40.3, 40.362. So it'd be about 6.7. So what we could write down here is that it takes a little less than 7 hours to drop to 40 milligrams. As you see, it was 6.7 hours, so it was a little less than 7 hours. Now, number 10, it says use either table or trace commands on your calculator to try and come up with a more accurate estimate of the time needed for the caffeine level to reach 40 milligrams. Okay. Remember how we was going down here? And I think I got it down here to like a little over 40.362. So we got it at 6.7. So what we could do here, we could play on this table. If it'll let me. Okay. Yeah, sorry about that. For some reason, the computer is acting a little finicky. So we could say, let me see. What was it again? It was 6.7. Okay, let's try 6.6. Okay, 6.6 was 41. 6.7, 6.8. Oh. We do 6.8, that's 39. Say 6.75. Let's see, 6.76. 6.74. So it's about 6.74. It's about 6.74 hours. Now, as far as time goes, we know this would be 6 hours, but we need our minutes. So it's almost like 0.75 of an hour or 3/4 of an hour. Or we could just put 0.74 and then we can multiply that by 60 minutes. And you see here, that's about 44 minutes, almost 45 minutes. So we could say about 6 hours, 45 minutes. So it's about 6 hours and 45 minutes. All right. Now we come here to our last page. It's problem number 11. It says make up a situation that could be modeled by each of the following exponential graphs. As always, extra points for creativity. Okay, if you look here, this graph here, we see exponential growth. We could say the popularity of smartphones, because smartphones didn't come out, I think, until like the early 2000s. So the popularity of smartphones. And here we could say this could be the popularity of flip phones. So those are just some examples. The answers can vary. So now we basically finished for 2.5 and 2.6. And then our next class period, we will go over 2.8. And if you have any other questions, feel free to contact me and have a wonderful day.